Welcome, medical data researchers, to a critical investigation in our machine learning series. I'm excited to be here with you, and today we're diving into a classification task using a powerful model and an explainability tool. I'm running this in Google Colab, breaking it down into clear code blocks so you can follow along as we analyze a dataset about breast cancer diagnosis. Let's get started by setting up our environment and gathering our tools for this health-focused mission. I begin by installing the Interpret library in Colab with pip3 install interpret. This library will help us with explainable AI, giving us insights into our model's decisions. Next, I import the essentials: NumPy for numerical operations, pandas for data manipulation, and matplotlib's pyplot for potential visualizations. From sklearn, I bring in load_breast_cancer to access our dataset, train test split to split our data, random forest classifier for our model, and accuracy score and classification report to evaluate performance. From interpret, I import ShapKernel from the black box module, our tool for local explanations, along with the show function to display results. I set up inline visualizations with setVisualizeProvider and inlineProvider, ensuring our plots rendered directly in Colab. I also set a random seed with np.random.seed42 for reproducibility. With our toolkit ready, let's load the data. I load the breast cancer Wisconsin dataset using sklearn's load_breast_cancer function. I create a data frame with the feature names provided by the dataset, 30 features like mean radius, mean texture, worst perimeter, and so on, and add the target column, where 0 means malignant and 1 means benign. I print data.head to take a look. The first row shows mean radius 17.99, mean texture 10.38, mean area 1001.0, worst area 19.0, target 0, malignant. The next row has mean radius 20.57, mean area 1326.0, target 0, also malignant. This dataset contains 569 samples of breast cancer tumors, with 30 features derived from digitized images of fine needle aspirates, measuring characteristics like radius, texture, and smoothness. The target is binary, 0 for malignant, 1 for benign, with 212 malignant and 357 benign cases, making it a binary classification task, which aligns with random forest classifier's capabilities, as it supports both binary and multi-class classification. Let's prepare the data for modeling. I split the dataset into features, and target X is all columns except target, including the 30 features like mean radius and worst area. These will help us classify tumors. Y is the target column, 0 or 1 for malignant or benign. I use train test split to allocate 20% for testing and 80% for training, with random state 42, giving us 455 training samples and 114 test samples, roughly 43 malignant and 71 benign in the test set, based on the dataset's 37 to 63 split. The data is clean, no missing values, and all features are numeric, so we're ready to train our model. I initialize a random forest classifier from sklearn with n_estimators equals 100 and random state 42. Random forest classification is an ensemble method that builds multiple decision trees, 100 in our case, each trained on a random subset of the data and features. It aggregates their predictions through majority voting to classify outcomes, reducing overfitting and improving accuracy, making it ideal for classification tasks like diagnosing breast cancer, where features may have complex, nonlinear relationships with the target. I call fit on xtrain and ytrain to train the model, letting it learn how features like mean radius and worst concave points distinguish malignant from benign tumors. Once trained, I make predictions on xtest with predict, storing them in ypred, and evaluate with accuracy and classification report. The results are excellent. Accuracy score is 0.9649 to 96.49% correct predictions, or 110 out of 114 samples. The classification report shows, for malignant 0, precision 0.98, recall 0.93, F1, score 0.95, support 43. For benign, 1, precision 0.96, recall 0.99, F1, score 0.97, supports 71. Macro average F1 score is 0.96. Weighted average 0.96. Strong performance across both classes, with a slight edge in detecting benign cases. I use ShapKernel from Interpret's black box module to explain our model's predictions. ShapKernel is an explainability tool based on SHAP, Shapley additive explanations, which approximates feature contributions for any model. In our case, a black box random forest. It works by sampling the feature space around a prediction, using a kernel-based approach to estimate how each feature impacts the output, offering local explanations that show why a specific prediction was made. I initialize ShapKernel with rf_model.predict_proba to get probability outputs, xtrain as the background data, and the feature names from x.columns. I generate a local explanation for the first test sample with SHAP.explainLocal on xtest.ilog0 and ytest.ilog0, named SHAP local explanation. I extract the explanation data with local explanation.data 0 and print the details. Predicted 1, benign, true label 1, benign, correct. Feature contributions show worst area at 0.0686. The strongest positive push toward benign, indicating a larger worst area aligns with benign tumors. Worst concave points at 0.0576 and worst radius at 0.0446 also push toward benign, while many features like mean texture and worst smoothness contribute 0.0. On screen, you're seeing the local explanation plot, a bar chart for this prediction. The worst area bar stretches right in orange at 0.0686, driving the benign prediction. Worst concave points and worst radius, also in orange, add 0.0576 and 0.0446. Features like mean texture, in gray at 0.0, have no impact. The final prediction of 1 is marked at the top, a clear breakdown of how features shape this diagnosis. Let's reflect on these outputs. They're a diagnostic report for our model. The head showed a tumor with mean radius 17.99, mean area 1001.0, worst area 19.0, target 0, malignant, and another with mean radius 20.57, worst area 1956.0, target 0, also malignant. Accuracy of 0.9649 means 96.49% correct predictions, 110 out of 114 test samples. The classification report details malignant 0 has precision 0.98, recall 0.93, F1 score 0.95 for 43 samples. Benign 1 has precision 0.96, recall 0.99, F1 score 0.97 for 71 samples. Excellent performance, slightly better for benign cases. The local explanation correctly predicted 1 for a true 1, with worst area 0.0686 and worst concave points 0.0576, pushing toward benign, likely reflecting larger, less irregular tumor characteristics, as benign tumors often have higher area values. Features like mean texture contributing 0.0 suggest they didn't influence this prediction. ShapKernel's local explanation gives us that XAI flavor, showing exactly how each feature contributes to this diagnosis, making our random forest decision transparent. To wrap up this medical investigation, we've analyzed the breast cancer dataset, a 569 sample study of tumor characteristics, and trained a random forest classifier, achieving an accuracy of 0.9649 and a macro F1 score of 0.96. The local explanation via ShapKernel revealed worst area and worst concave points as key drivers for a benign prediction, offering a clear view into our model's reasoning. Random forest classification's ensemble approach captured complex tumor patterns, and ShapKernel's SHAP-based method provided transparency for our black box model in this binary classification task. Grab this code, experiment with feature subsets, and dive deeper into cancer diagnosis. I'm inspired by this health-focused analysis. Hope it's got you thinking about data's role in medicine. See you next time for another life-changing data dive.